work done by force applied. So firstly we'll say work done by the force applied equals to the force of applied multiplied by delta x and the cos of theta. Then the force applied must be and the displacement and this one. And then now let's check our theta. So theta in this case, let's draw our free body diagram with the of motion. So this will be the direction of the motion. So if the direction of the motion, and then there is also the force applied. So this will be the force applied. Now, I'm going to measure angle between the green and the red. So obviously there is no angle there. So what is not angle? The angle is 0. So if we calculate the force, the work done. So if we calculate the work done by the applied force, then it means the work done by the applied force multiplied by delta the displacement. Then we're going to have the cos of 0 degrees. And then that would be a formula for calculating the work done by the applied force. And then again, these two still they are the normal force and the gravitational force. So let's put it the normal force and the gravitational force. So the angle between the motion and that is still 90. So they are not and hence then we're going to say work net equals to work of normal force plus work of gravitational force plus the work done by the force applied. But we agreed regarding this is 0 plus 0 plus work done by the force applied. So the work net done on this object is the same as the work done by the force applied. So this one, as long as the object is on the horizontal motion or horizontal surface, then the work done by the friction and the normal, then it means I is 0. It's not valid. Then let's get to number 2. This object now is on a rough surface. And then here we have rough surface. And let's decide or is pulled in that direction with force F, and then it will move this delta x. Like this. So this object will move for this delta x and then it's pushed in that direction. So this is the direction of the motion. Direction of motion. And then once it's a rough surface, it means there is a frictional force. So in this case, if there is a frictional force, then it means let's do our free body diagram. So in this case, our free body diagram is normal force, gravitational force, and of course there is force applied in that way. And then, so I'm drawing like this because my surface is horizontal, so I must put everything under horizontal form, which is the applied force. And this one, so I apply under horizontal. So this is my force applied, and of course there is a frictional force that is opposing the motion of the object. So again, the direction of motion. Let's draw another free body diagram. This one is for me to identify theta. So this is the motion, and if I draw my normal force, there is 90 there. Gravity, there is 90 there. So meaning the two rolling are the anyway. And then the angle between the force applied and this one, which is the motion, is 0. And then it means this is the frictional force, and then the angle between this motion, the green one and the black one, is 180 degrees. So that is how to get my theta in a nutshell. So let's write the formula for calculating the work of. So in this case, the work done by the force applied equals to the force applied multiplied by delta x, distance will be moving from here to here in meters, and then the cos of theta. Now work done by the force applied equals to the force applied and the delta x cos. Now what is the angle between the force applied and the motion? The angle is 0 degrees. Then you substitute your force applied, the distance, and then cos of 0 degrees is going to go for 1. So if you multiply that, we get the answer. Then the work done by frictional force equals to force of friction multiplied by delta x and the cos of theta. Now the work done by frictional force equals to force of friction multiplied by the distance and the cos of theta. Then in this case, angle between motion, the green one and the black one, is 180 degrees. So we'll have 180 degrees, so will be minus 1, and then multiply by the answer. Then the answer of the work done by friction will be negative. And then of course, if we are looking for work, so we're going to work net in this case. So work net equals to now the normal force and the gravitational force are for 0. Then we'll say this will be the work done by force applied plus the work done by the frictional force. So when you substitute, you just substitute the answer U equal more, and then the answer U equal more. This positive is for formula. When we say net, we add all the forces, but the force join forcing working with le sign here, and then you substitute and then you get the correct answer for the work net. Right, here smooth surface, force applied horizontal to the surface, force applied horizontal to the surface with the rough surface. Now let's check when the force is applied at an angle. So now 5 kilogram. Now a force is applied at an angle this way. So let's just give it a number, 15 degrees, and the object is displacing this way. This is the motion, and let's say this is a smooth surface. Right, on a smooth surface. Now let's start by drawing free body diagram if we need to calculate work. So free body diagram, normal force, Fg. Now our force is applied at an angle. Can we name it F? So this is F. Or we can say F applied. So that is F. Then in this case we will have again, let's draw another free body diagram for determining theta. Now the other free body diagram, this is what we have. Again, this is our motion. Now having motion this direction, and then so our normal force again is giving us 90. We don't include on the work net. Gravity is also giving us 90, so we don't include. And now we have our form in this way, and angle between here is named to be 15 degrees. Right, now let's do our formula for work done by applied force. So we'll say the work done by force applied equals to, then the force done by the applied, and then delta x, then the cos, then we said the cos of theta. Now the work done by the applied force equals to the force of applied moving in that distance. Now the cos, what is our theta in this case, is angle between the motion and the force applied, which is F here, and the angle between that is 15. Then after substituting that 15 degrees, then we can substitute your force applied and the displacement at which the object is moving. So maybe it's moving from here up until here, which is named delta x. The distance, maybe it can be 2 meters or 2.5, any distance that it can move. Then that's how we'll get the work done by the applied force. So again, it means the work net here, because this is the only external force that is applying. So we'll simply say the work net equals to the force, work done by the force applied. So S will be the only one that is moving there. Right, now let's include friction on the force that applied in that angle, and then let's see what we have. Right, 5 kilogram, and then it's going to displace. Now this time let's write delta x to be 5 meters, and this is applied in that way, which is F, and then how much, let's use 15 degrees again. And now there is a rough surface. So if you are not saying rough surface, so if our rough surface, so what a kinetic frictional force is acting on the object, maybe between A and B. Now let's do free body diagram. Oh, direction of motion. So the direction of motion, the object is still moving in that way. So moving in that way. So let's draw a free body diagram. Free body diagram. Normal force, frictional force. Of course, there will be frictional force, and there is the force applied. Again, our free body diagram of the calculations of the theta. This is the motion, and now after having the motion, then we are having our normal force being 90, gravity being 90, angle of 90, and then our force happening that way, which is 15 degrees between here and here, and this one, which is the frictional force, and the angle between here to here, is 180 degrees. From this point, 180 degrees. So now let's do the work done. So normal force and frictional force, they are 0, so we can just write them. Work done by normal force equals to 0 joules. Work done by frictional force, in this case, will be 0 joules. Then let's have work done by applied force equals to force of applied, equals to work, force of applied, moving for delta x, which is 5 meters in this case, multiplied by the cos of theta. Now work done by the force applied equals to force applied multiplied by the displacement, the cos, angle between the motion and the force is what? Is 15 degrees. Now the work done by frictional force equals to force of frictional force moving for delta x, the cos and the angle between frictional force and the motion is 180 degrees. And then if that is the case, then it means the work net equals to work of force applied plus the work of the frictional force. Then that will be the net work done on this object as it's moving in that way. So rough surface, applied force, and then there is frictional force. So this is the work net done on this object. Right. The other scenario. So in fact, these are the scenarios of the object that is pulled on a horizontal surface. So they are pulled in that way. So we are looking for other scenarios, and then what is left is to move to an incline scenarios. So meaning within the present of friction, the force at an angle at an horizontal, and then the force applied with the rough surface. So this is what we have for the horizontal incline. So I hope you can now be ready to calculate the work done on an horizontal surface. So that will be it for horizontal surface. Then now, before we move to the incline, then I think we can include the work energy theorem, including the velocities.